Hello, students, and welcome back to our next lesson on the electromagnetic waves topic. But we left off yesterday, if you recall, with the electromagnetic spectrum. The electromagnetic spectrum, if you recall from yesterday, is made up of the various wavelengths of electromagnetic waves from longest to shortest. But today we're going to be narrowing in and focusing on one portion of the electromagnetic spectrum, and that is the visible light portion of the electromagnetic spectrum, the portion that our eyes can detect. As human beings, our species is very visually oriented. And as we begin this final unit of study on astronomy, we're going to be relying a lot on observations made with our eyeballs. And the best place to start with that is to focus on visible light. So today we're going to explore some basic information about the visible light portion of the electromagnetic spectrum. So let's dive right into it in our notes and define what visible light actually is. Visible light is energy, and remember we talked about that yesterday as far as energy being the source of a disturbance traveling from one place to another. The energy in a range of the electromagnetic spectrum that can be seen with our eyes. Now, it's a mouthful, but what does it mean? Well, the electromagnetic spectrum, this range of wavelengths that are being emitted from many bodies in space, including, the stars, etc., that we mentioned yesterday, but are also being emitted by things even in this laboratory, like the lights from the ceiling. There's a whole range of wavelengths that are being emitted, but our eyes are sensitive to only a certain portion of those wavelengths. Even though the other wavelengths, radio waves, are going through our bodies right now, there are X-rays from the sun that are actually traveling through our bodies right now, but we can't see those with our eyes. We can experience those in other ways. If you tune a radio, you can tune into a radio station and hear them, but we see a certain wavelength range with our eyeballs, and that's what we're focusing on here today, the visible light. And so the visible spectrum, there's a great way to remember it. It's called Roy G. Biv. Perhaps you've heard that mnemonic or memory aid in the past, Roy G. Biv, but I want to tell you a little bit more about it here in science class. The visible spectrum of colors ranges from the longest wavelengths to the shortest wavelengths in order: red, orange, yellow, green, blue, and violet. And we summarize that with the letters Roy G. Biv. Now, here's the deal. Some of you might be saying, hey, wait a minute. What about indigo? What about indigo? Yeah, let me tell you a little story, okay? Many, many years ago in the 1600s, when Isaac Newton was first exploring light in great detail, and he did some famous experiments with prisms and divided light, white light, visible light, into the spectrum of colors that we call the rainbow. Back in his day, there was a lot of interest in numerology, and there were a lot of superstitions, you might say, that weren't necessarily scientifically based. One of the things that Isaac Newton was convinced of is the number 7. Number 7 was viewed by many as a number of perfection. And there are many examples of that throughout history. But here's the deal. When he used his prism to divide light into the colors of the spectrum, he saw the red, orange, yellow, green, blue, and violet. And if you add up those colors, it adds up to 6. And because he was convinced that the number 7 is a number of perfection, well, he added a 7th color, indigo, which is a color between blue and violet. He could have added another color between, he could have added turquoise between green and blue, or lemon color between yellow and green. You get the idea, right? But he tried to squeeze in a 7th color because he thought this was just so cool. This was a sign, this rainbow was a sign of perfection, and you had to have the number 7 associated with it. So even in art classes today, when you learn about Roy G. Biv, they insert the I for indigo between the blue and the violet. But in science today, we recognize that there are 6 distinct colors of the rainbow, and we're going to stick with 6. It's not a magical number in any shape, way, shape, or form, but we stick with 6 colors. So, hey, it's one less color for you to memorize for the quiz, right? So, Roy G. Biv without an I. So these are the colors of the rainbow, and actually from an artistic point of view as well. There are 3 primary colors and there are 3 secondary colors. You learn that in art, and 3 plus 3 is also 6. But be that as it may, it was Newton who came up with this observation, this brilliant observation, that the visible spectrum, when it's all squeezed together, forms white light, the visible light that we see. But it can be stretched out with things such as a prism, which we'll be playing around with later on. So let's talk more about visible light. We have learned a lot since Newton's day in the 1600s. And one of the things that we have learned in the last century is that light is not only a wave, an electromagnetic wave, but it's also a particle. And the particles that make up light are called photons. It hasn't been until the last 100 years or so that we have actually recognized light as acting as both a particle and a wave. And we'll explore later the interesting connections that makes to the rest of our study of the universe, this unit. But for the time being, know that photons are what we call the particles of light. And you've seen the radiometer in the classroom, and that radiometer, when the sun is shining, actually starts spinning around. And that's because photons are pushing on the one side of the blades in the radiometer. Pretty cool. Hopefully we'll have a sunny day so that you can see it spinning around. If not, I'll show you with a light shining on it. All right, so back to light. Not all visible light is the same. In human society today, we have a number of artificial sources of light, and I want to talk about those right now. Natural light we get from the sun during the daytime hours, and visible light from the sun is a full spectrum of colors that shines on planet Earth and everything else in space. Other sources of natural light could include fires. Candle flames emit light. But in the last 100 years or so, maybe 140 years now, human beings have developed some forms of artificial light. First one is incandescent. Thomas Edison, who did a lot of his work in New Jersey, In fact, the Edison Labs here in New Jersey is where Thomas Edison developed the filament, the wire inside the incandescent light bulb, which revolutionized the world as far as doing work at night, because his light bulb made it economical and feasible to illuminate the darkness of nighttime. Well, incandescent light bulbs, and they're being phased out now, so some of you may not even be familiar with incandescent light bulbs, but incandescent light bulbs have a filament, which is a small wire, typically tungsten wire, that allows electricity to pass through it. And as electricity passes through the wire, it heats up. In a similar way, if you have a toaster at home, maybe you've made toast. Anybody like toast? I like toast. If you ever looked inside a toaster when it's heating up that bread, you may see those wires on either side of the bread turning red or orange because of the electricity passing through them and the wires heating up. They're giving off a certain wavelength of light that you can see because of the temperature of those filaments. Same with an incandescent light bulb. As electricity passes through that tungsten wire, the wire heats up, and it heats up really hot. And generally speaking, this bulb is a vacuum, so it doesn't burn up, it just heats up. And that heat produces light. These types of bulbs are not very energy efficient because a lot of the energy that we want to be transformed into light energy first has to be turned into heat energy. And if you've ever changed one of these light bulbs, you may have actually burned yourself because they can get awfully hot. So incandescent light bulbs produce light from heat. That brings us to the next form of artificial light, and those are fluorescent lights. Now, until recently, just this year, we got rid of our fluorescent lights in the laboratory. We've always had fluorescent lights here, and there are still some fluorescent lights that exist in the school, but we've slowly been getting rid of them, and the lights that we now have are LED lights. I'll talk about those in a moment. But fluorescent lights, maybe you've seen these spiral tubes or these long cylindrical tubes. These fluorescent lights work in a different way from incandescent lights. Fluorescent lights actually allow electricity to pass through a gas inside this tube. Whether the tube is coiled or straight is really irrelevant, but the electricity is allowed to pass through a gas inside the tube. That gas, when energized, emits a certain wavelength of light, ultraviolet light. Now, if you remember from yesterday, unless you're an insect, our eyes can't see ultraviolet light. And so some of you might be thinking, well, if they emit ultraviolet light, then how do they make light that we can see from? Here comes the second part of a fluorescent light source. There is a phosphorescent powder that is coating the inside of the glass of fluorescent bulbs. And the ultraviolet light makes those phosphorescent chemicals glow in a different wavelength of light, visible light, that enables us to see. Now, this will be the first year that we aren't able to do this experiment. Normally, after this lesson, we use a device called a spectroscope, and we look up at the fluorescent lights, and we see something really cool. I'll have to get my hands on a fluorescent light for some experimentation tomorrow because, well, stay tuned. I'm going to talk about spectroscopes in a little while. But this brings us to the third type of artificial light, which is neon light. And I mentioned neon light for a couple reasons. First, it's just pretty cool. How many of you have ever seen neon lights? If you've ever been to a restaurant or a city with signs on the windows, you probably have seen neon lights. Now, neon is a particular element on the periodic table. And if you look at the periodic table in the back of the lab, you'll see it's right underneath helium, right above argon. It's right next to fluorine. It's one of the noble gases, that last column of elements on the periodic table. Neon is an element. And neon, in addition to helium, argon, krypton, xenon, and radon, the other elements on the periodic table in that family of elements known as the noble gases, they're inert, which means they don't chemically react with other things very readily at all. But these gases have interesting properties to them. When you send energy in the form of electricity through these gases, they glow different colors. Neon glows this color, kind of a reddish orange color. But I'm sure you've seen other neon lights of different colors. It's because they're filled with other elements, the gases of other elements, because different elements shine different colors, which is pretty cool. So calling all of those kinds of different colored glowing lights neon lights is really scientifically inaccurate, because only the red ones, the reddish orange ones, are filled with neon. Other ones are filled with other elements, as we will explore tomorrow in the laboratory, because we're going to be seeing these energized gases of different elements, and we're going to be examining different colors with a tool called a spectroscope, which we're going to talk about in a moment. But generally speaking, all of these energized gas tubes are called neon light. All right, let's move into something else here, which will help prepare us for tomorrow's fun laboratory activity. How many of you have ever watched a crime show? Okay, probably a good number of you. If I were to ask you, how can you identify someone at a crime scene that they were at? You might suggest, well, you could find fingerprints at the crime scene and match those fingerprints up with the identity of criminals that you know. And that would be a very good detective answer, because everybody has unique fingerprints. Everybody. In fact, as you may know, I have identical twin daughters. And my daughters have the same exact DNA. They're identical to one another. And so if they committed a crime and they left behind some DNA, one of them could do a crime and blame it on the other because their DNA is the same. Not that they would commit a crime. At least I certainly hope not. My goodness, that would be terrible, and I would scold them for doing so. But even though they are identical twins with the same DNA, my daughters have different fingerprints, because that's not determined by DNA. So even identical twins have unique fingerprints that can identify them as themselves. Now, why am I talking about crime scenes and fingerprints? Well, here's a really cool thing. As we are going to discover tomorrow in the lab, every element that becomes a luminous body, in other words, if a body like a star has enough energy that it glows, gives off light, that's what a luminous body means, if it's giving off light, every element that is present glows with a different, unique fingerprint. This is something we can do in the laboratory, and we'll do it in the laboratory. We will see that different elements, when glowing, produce different colors. Incidentally, it's how you get different colored fireworks on the 4th of July. If you get green fireworks, that's a result of the element copper. Copper glows green. If you have red fireworks, that's the result of strontium. Strontium glows red. If you have white fireworks, that's the result of the element magnesium, because magnesium glows white. The point is, every element has a unique fingerprint that we can see using a spectroscope. And these spectral lines that I'm referring to are the specific wavelengths of light, or the fingerprint, emitted by a luminous body. I have a poster in the room that we've referred to that looks something like this. It has different elements. The elements have the spectrum of light spread out so that you can see only the very specific wavelengths of light, the fingerprint, if you will, of that element revealed. And this is what our lab tomorrow is going to enable us to do. It's going to enable us to spread out the visible light so that we can see individual color bands, so that we can identify the fingerprint of an unknown element. Have you ever wondered, how in the world do astronomers know what a star is made up of that's billions and trillions of miles away from us, and there's no way that we can possibly go there and get a sample from it, bring it back, and analyze it in the lab? We don't have to, because we've already done lab analysis with different elements using spectral lines, and all we need to be able to do is see the star with a telescope. Hook up one of these instruments called a spectroscope to it and examine the spectral lines. We can use these spectral lines to identify unknown elements from immense distances away from them. So I think personally it's pretty darn cool that an astronomer here on Earth can look at a star millions of light years away and be able to tell us, well, this star is made of this amount of hydrogen, this amount of helium, this amount of this element and that element, simply by looking at it through a telescope. I think that's remarkable, because the laws of the universe exist throughout the universe, and the fingerprints of light don't lie. The universe is like a big crime scene, and astronomers are like the detectives to find the clues and make conclusions. So I've been making a lot of reference to this thing called spectroscopes, so let's look at it a little bit closer. Spectroscopes are instruments used to observe spectral lines. So in this diagram here, we see a luminous body, in this case a star. The light travels through a spectroscope's prism. A prism, like Isaac Newton's, rips apart or spreads out, like your home activity, spreads out the visible light into a rainbow of colors, Roy G. Biv, and in that spectrum of colors, some of the colors will be brighter or darker, specific wavelengths of light that we will be able to see, and you'll determine tomorrow in the lab. But a spectroscope is an instrument used to observe spectral lines. This is another example of a more complicated spectroscope. Part of it allows the light through and an observer to look in one side, another observer in another side, and you can see the very specific bands of light. The spectroscopes that we will be using tomorrow look like this, just like the picture shows. And on one side of the spectroscope is, I don't know if you can see this all that well, but there's a little slit that will be up and down. This side enables the light to be seen with your eyeball. Your eyeball goes up to the slit side. There we go. Now we can see it a little bit better. The other side has something on it called a diffraction grating. This diffraction grating is a clear piece of plastic with millions of microscopic prisms engraved in it. Now, if you look at it on the camera right now, you can see kind of a rainbow of colors as I go back and forth as it is reflecting the light from the laboratory. You can see the different colors of light. But what we will be doing is aiming this diffraction grating to a specific light source. We'll put our eyeball up to the other side, the little slit, and inside we're going to see Roy G. Biv. But we're not going to see the full spectrum of colors. We're only going to see very specific wavelengths. Now, here's another example of a spectroscope that we will be using. And when you look inside this spectroscope, you will actually see numbers on a graph that show exactly what the wavelengths of light are that you are looking at in order to make a spectral analysis. Spectral analysis enables us to determine the composition of various things. And spectral analysis is used not just in astronomy, but it's actually used in crime scenes. There are devices where scientists, detectives can put unknown elements, particles of some kind, into a spectral analysis unit, and light will travel through it and produce a graph with spikes on it. And these spikes in certain wavelengths of light enable the device to determine exactly what elements make up a particular substance. So, spectral analysis, which is what our lab tomorrow is going to be all about. Spectral analysis is used to determine the composition of stars and planets through reflected light off of a planet far, far away. And it basically works in this form. We have a star shining light. That starlight filters through. If we were looking at a planet, for instance, and we are observing lots of exoplanets, which we'll talk about in a future topic, but planets beyond our own solar system, we are now able to view light passing through the atmosphere of planets far, far away through a spectroscope, and it produces a spectrum of colors. And in some units, they use what's called an absorption line spectrum to do this, which means there are certain wavelengths of light that determine the exact identity of the elements that can be found in the atmosphere of planets billions of miles away from us. And by knowing the elements that exist, we can make predictions as to whether that planet might harbor life or not. We'll talk more about that in the future as well. But the idea of spectral analysis is that it uses the spectral signature of elements. Remember, the spectral signature of elements are like the fingerprints that are unique and distinctive to certain elements in the universe. And so again, we're going to be exploring spectral analysis in the laboratory tomorrow. And you know what? I think we'll end this video here for today. The next time we meet will be a brief video before the lab explaining the procedures that we will follow in order to enable us to be astronomical detectives and use spectral analysis to identify unknown elements in the universe. So until then, stay tuned. And for now, I'll say bye-bye.